Good day, grade 10. So in our section on sound, we also need to know how to use the wave equation. Let's just remind ourselves what the wave equation stands for. So first of all, V is velocity or speed of sound. Okay, and it's measured in what? The SI unit is meters per second. Lambda, so that's V. Lambda is our wavelength, the length of the wave, and that is measured in, the SI unit is meters, and F is frequency, and that is measured in hertz, HZ, hertz. Right, so now that we've realized what the wave equation stands for, there are a couple other equations we need to know and to remind ourselves of. The first one is T equals 1 over frequency. T is what? It is our period. That is the period of the wave, and it is measured in seconds, and the period is inversely proportional. In other words, it equals to 1 over the frequency. So F is our frequency, which again is measured in hertz. Right. Old one that we know about, speed is equal to distance over time. And distance again, SI unit is the meters, and time again is seconds. So now let's look at a couple of uses of sound. The first one is our echoes. We know that sound in certain situations echoes. In other words, it repeats itself back. It reflects off surfaces. One of the most useful uses of sonar is, for example, in the situation here where you've got a boat and it's trying to find a submarine. There are lots of other ways that you can use sonar. For example, if you are a fancy fisherman, you may have a sonar that tells you where all the fish are. But we got this from nature. In nature, echoes, and the use of echoes is called echolocation. And here's exactly what happens. We have bats that send off a signal. It gets reflected by the flying insect to the bat, and the bat has got this amazing ability to use those reflections to tell not only how far the insect is from it, but how fast it's traveling. Similarly, dolphins do exactly the same thing. They use echolocation to find out where the fish are. So we have copied nature. Now we can use the wave equation and all the equations that we've gone through now in a couple of examples. So let's look at a couple of examples. First of all, it says, a ship sends a signal to the bottom of the ocean to determine the depth of the ocean. So the ship wants to know, is it going to sink? Is it going to hit the bottom of the ocean? Wants to know the depth of the ocean. The speed of sound in water is 1,450 meters per second. If the signal is received 1.5 seconds later, how deep is the ocean at that point? Right, so I've kind of helped you already because it says the step one, we need to identify what we've been given and what is asked. So what have we been given? We've been given the speed of sound, We've been given the speed of sound in the water is 1,450 meters per second. We've also been told that the time it took to get there and back, is 1.5 seconds, and it asks how deep is the ocean. So what are we looking for? We're looking for the distance. Now that we've identified what we have and what we need, we can actually now calculate the distance. So we know that speed equals distance divided by time. Therefore, we know that distance equals speed times time. So we can take our 1,450, let's just do that, 1,450, and we can times it by our 1.5 seconds, and we end up with a distance of 2,175 meters. But is that really how deep the ocean is? No, because that was the time it took to get both down to the bottom of the ocean and both back up. So what we've done is we found double the distance. So what we now need to do is divide this answer by 2, and the actual distance is 1,087.5 meters. That's how deep the ocean was at this point in time. Okay, the other way you could have done it was divided the time at this point. Instead of timesing it by 1.5, you could have times it by 0.75. Either way, I don't mind which way you do it, as long as you understand that the time taken in this question was both for the down trip, down to the bottom of the ocean, and back up to the receiver. Let's look at another example. A man stands between 2 cliffs, as shown in the diagram, okay, and claps his hands once. Assuming the velocity of sound is 330 meters per second, okay, what will be the time interval between the 2 loudest echoes? What will be the time interval between the 2 loudest echoes? So let's think about what we've got here. We want to know how long it takes for the sound to get there and back. But we also want to know how long it takes the sound to get there and back, right? So let's have a look at that. They've told us that V equals 330 meters per second. Again, we're going to be using the equation that speed equals distance divided by time, but we're going to rearrange it, and we're going to say time equals distance divided by speed. But now for the first cliff 1's echo, our distance isn't just 165 meters. In fact, it's 165 times 2, because we have to get there and back. So the distance is 330 meters. And the speed is 330 meters per second, which equals the time. So in this case, the time it took to travel, the echo to travel from the man to the cliff and back was just 1 second. Right. Now let's look at cliff 2. Cliff 2, the distance was 110 times 2, because we've got to go there and back. So that's 220 meters divided by the velocity again of 330. So what does that become? It becomes 220 divided by 330, and it equals, if you did this on your calculator, you'd have got 0.6666, but remember we round off to 2 decimal places, so it's 0.67 seconds. But what was the question? The question was, what was the time difference between the 2 echoes? This echo would arrive first, this one here, and it would take a time of 0.67 seconds. This echo would arrive second, because it's taking a time of 1 second. So the time difference would be 1 second minus 0.67 seconds, which becomes 0.33 seconds. So that's what he'd hear. He'd hear clap, and then 0.33 seconds later he'd hear the echo of the second clap. Admittedly, that's quite a lot bigger of a time gap than our 0.33 seconds. Is a third of a second. Right, grade 10s, I hope you now know how to use the wave equation and the speed equals distance over time equation to work out how to work out distance when it comes to do with problems with echoes.